In this lecture, we are going to talk about data space and data manifold. We just want to explore the nature of data as and how we represent data, right? How our data is being represented in our machines, and how are they distributed in this space that we use to represent them. Okay, first do a little exercise. Okay, so look at this code, right? What does this code do? I really encourage people to spend time, make this code and run it. Okay, so you should you can pause the video and then make this code. There's only nine lines of code, right? And then run it and then experience for yourself uh, uh, about this code. Okay, so yeah. So I believe that you have run this code, you have make this code and run, and what do you see? And what does this code do, right? So you can see line 6 is a for loop from I in range 0 to 9, right? Range 10, right? 10 times, right? For loop 10 times. Line 7 is really a random number of numpy random, right? Of 28 by 28, that means making 28 by 28 pixels, an image with 28 by 28 pixels, a random pixels, right? Random gray level, okay? Okay, image IMG is a random image. Line 8 really plot, show this image. So when you run this code, you will see random image, essentially random image, right? Would you ever see a image that looks like, say, a digit, right? 28 by 28 pixels, right? MNIST data set is 28 by 28 pixels. It's a digit data set, handwriting digit, right? Or would you see a smiley face? Or would you see anything like any digits or any numbers in any language, like in the Chinese language, in the Arabic, numeric, in whatever, or English letters? Will you ever see that? Say you do this line 6, you do this 10 times. Let's say you do 100,000 times, right? Will they ever see that, right? What's the probability of randomly generate an image and see something sensible other than TV noise? Yeah, you may want to pause the video a little bit and do this experiment, I don't know, 100 times, 1,000 times, whatever. And just have a sense of your chance of getting something that look like something that we can recognize other than TV noise. I think your chance is very low. You can try, yeah? Okay? So what is this telling us? This telling us that the space of image is very sparse. Space of recognizable patterns in this 28 by 28 gray level is super sparse, very sparse, right? Okay. Okay, let's look at this data set. What's wrong with this decision boundary? This one we get from TensorFlow Playground. We have blue dots, yellow dots, and then we draw a decision boundary across a straight line across. What's wrong with it? What's wrong with the data and what's wrong with the decision boundary? You may want to think a little bit. Also pause the video and think about this. Okay, we'll come back to this shortly. Okay, another example. This is the weight and height of people. Okay, one spot represent one person. Some people are quite short, 120 cm. Therefore, they don't weigh so much, 40 kilogram. Some people are very tall, 2 meters, and they weigh a lot, right? 90 kilograms or even more. So there is a trend. Nature and biology tell us there's some trend in this data set. The biology of human beings mandate that all these data points must fall between some range. Okay? For example, you don't get someone who is 2 meters tall and only 40 kilograms, like this red point here. Or you don't get someone who is 120 cm and already 90 kilograms. You don't get that because biology and nature doesn't allow that, right? So there's certain pattern to data that certain pattern that data must obey. And what are these patterns? Patterns is the underlying biology, science, physics, mathematics, economics, underlying laws of nature that generate the data, right? Okay, so for this reason, if we represent the weight and height as a two-dimensional space, a lot of this space is actually empty. Okay, just like the two red points, it's just not possible. Biology just doesn't allow that, right? The space at the two red points there is no human beings at the space at two red points, right? For example, right? Coming back to here, the space of 28 by 28 grayscale pixels image. This space is this space is very huge, right? Right? 28 by times 28 dimension is very huge. But the reasonable pictures image that we can recognize in this space is very, very little, only a tiny, small little fraction, right? Okay. So again, what's wrong with this division boundary? We're back to this, right? This is artificial data, two blobs, two Gaussian. So the question is that we should ask is why the decision boundary must be a straight line. Okay, right? What's wrong with this decision boundary? Why must it be a straight line? Why can't it be something else other than straight line? Okay. Okay. Another example, some hypothetical data, the black dots and the red dots. Now we have labels like black or red. Okay, x1, x2. The data representation is a two-dimensional data representation. But what we want is the data lies in some special pattern with some special location in this space, right? This space, again, mostly empty, data is somewhere. How to draw a decision boundary for this kind of data? Maybe like this. Okay, fair enough, reasonable enough. But what's wrong with this? Or maybe because you want, yeah, the same. What's wrong with this, right? This similar situation here. Huh? Maybe you want to draw a decision boundary like this. Drawing a decision boundary like this make more sense because it's just separate the red dots and black dots. Everywhere else, it doesn't know how to separate it, right? Logically, right? Then if I have a blue dot, this is a blue dot, then we want to ask a question. Is a blue dot, blue data, black, belong to black class, red class, or unknown? Okay. Some of us will think, okay, it doesn't belong to black class, doesn't belong to red cluster or black cluster, so it's unknown, right? This is reasonable, right? If we draw the decision boundary like this, the blue dot immediately belongs to the black cluster, okay? If if we go into a high dimension, one dot is one picture. In this case, it's high, very high. Let's say CIFAR 10 is 3072 dimension, right? High dimension space. Okay. In this case, in the high dimension space, as we discussed, most of the image space are just TV noise. There's just a small fraction of pixel combination that make up an image that we recognize. Cats are represented by black dots. Red dots are represented by red dots. How about the blue dot? The blue dot would have been what? Look like what? It look like some TV noise, right? With RGB colors, suppose, right? I think people will agree with me on this, right? The blue dot is far away for any reasonable image, therefore it looks like TV noise. If we draw a decision boundary like this, then we are just saying, oh, it's a cat. Okay, it's a cat. Okay, that doesn't make sense. Okay, or we could have drawn a decision boundary like this. Is equally good. Training errors is could be roughly equally small, right? Why would this decision boundary be better than this? Okay, come back to that question here. What's wrong with that decision boundary? This decision boundary is equally good as the previous one, or the purple line could have been a good decision boundary, or this decision boundary would be equally good. Okay, so yeah, I think you can try this just for fun, right? You can make this network. This is what we call, maybe I can call it overspecified. Or I have lots of nodes, lots of hidden layer, lots of weights and lots of bias. And then I want to classify a simple data set, right? You can try rule, hyperbolic tangent, so on and so forth. And just try and experience and see what decision boundary you will get. Yeah, and try several times, right? Okay, one last example, right? This figure shows points on a 2D plane. Obviously, it is red points and blue points on a 2D plane. Each point is represented by two numbers. Okay, X and Y, two numbers. Then I ask the question, how many dimensions is this data? Okay. The obvious answer would be, naive answer, obvious answer would be 2. Each point is represented by two numbers. The question is, do we need two numbers to represent these points? All these points, do we need two numbers? Because there is a pattern. Okay, there is a pattern. When there is a pattern, the dimension of data is probably less. Okay, there's a pattern here, right? Do we still need two numbers to represent this data, right? And how do we draw a decision boundary across the blue and the red dots? Maybe like this, okay? Or maybe like this. These two decision boundaries are equally good. Okay? If I overlay these points on a sine curve, straight away you can see the patterns. Right? It's a pattern, right? And then we can conclude that, oh, all the points can be described, can be sufficiently described by one number, t, right? Where x is t and y is sine t. And all the xy point represented by 1t. Okay, so for this data, although it's embedded in some two-dimensional space, is really a data can be represented by one number. We call this one-dimensional manifold. Right? Okay, this data is all the points sufficiently represented in a one-dimensional manner, although the points itself are encoded using two numbers, x and y, but the variable t is enough to represent them. Okay. Okay, with this, I hope I have made myself clear about data space, and data manifold. Right? Data usually lies in some kind of manifold because inherently there's some patterns. And the way we represent data is in many cases highly inefficient. For example, image data, the way we represent image data is highly inefficient. Most of the image, most of the space that we use to represent image is just TV noise. Okay, with this, thank you. Thanks.